today we will start our discussion on routing. Okay. Actually, we have already talked about routing a little bit in different contexts, specifically in the context of ATM, how the ATM virtual path etc., are set up. But today we will talk about the major area, we will start our discussion on the major area of routing, which is how and specially with reference to the TCP/IP stack, that is how packets are routed in an IP network. So, we will talk about today we start the introduction to routing, and then we will take up the discussion about different routing protocols in next set of lectures. Okay, so let us just recollect what is the job of the network layer, or what is routing. This is to carry data end to end, that is from the source to destination, perhaps through a number of intermediate subnets. Now, depending on whether connection oriented or connectionless services are used, other functionalities may be incorporated at this layer. We will talk about this later on. Right now, we are talking about pure IP routing of IP packets, and how you can have a virtually connection oriented system on that. We will discuss it later on. So, the point is, I mean, unlike data link layer, if you remember, is just the next hop, just the link which is immediately adjacent. So, that has some advantages in the sense that whatever information you require about it are locally available. Here in routing, the major problem is that we are now talking about routing over multiple networks and towards a very remote system, and the packet might have to take many hops, okay, maybe 10, 20, even 30 hops to reach the end point. Okay. And when you take naturally say let us say 20 hops, the area you are sort of serving becomes so large with so many machines connected to it, and how do you keep track, and then naturally with so many machines with so many links, the problem is some of the link may go down, some of the machines may go down, some of the machines may come up, and when I say machines, it may refer to actual either PCs, servers etc. They may also refer to the network boxes like other routers, alright. So, the job of the router is to know that locally which link I should take, so that globally the packet will go arrive at nearer to its destination in some sense, alright. So, this is the basic routing problem. At a particular subnet node, given a packet with a particular final destination, determine the next subnet node or the outgoing link which is appropriate. In datagram network, this is determined for individual packets. In VC networks, this is determined only for setup packet for each session, alright. So, we will concentrate on the datagram network. So, objective, consider a router X. X may not know the topology of the entire internetwork. Okay. You see, in these days all I mean everybody wants to be connected to the internet. So, we have a giant network of networks, alright. So, there are there is this big giant network of networks spanning the entire globe, and then in a particular network once again it may be divided into so many sub networks, and you will have to, and there are millions even billions of machines connected to this network. So, some user somewhere wants to connect to another user on the other part of the globe, alright. So, this is a huge problem, but how to solve it in a systematic fashion, but this is the objective of the routing or the network layer. So, X needs to determine the next hop router for every other network in the internet. Now, why are we talking about network? After all, we are trying to reach some particular machine, maybe some particular let us say server. Well, if you want to keep track of all the machines in the world, that becomes really intractable, that becomes really very big. So, we reduce the problem somewhat, that means all these different machines, they are grouped into different what are called networks or even sub networks. So, let us use the term network for the time being. So, they are grouped into different networks, so that a remote router need to keep track of only the remote network rather than a particular server in that network. Okay. So, that makes the problem somewhat smaller and somewhat more tractable. Okay. So, we want to determine the idea of course is that once you reach that remote network, your destination network, now within that network finding that particular server will be very easy. Okay. As we know that either through ARP or some such protocol, they would know how to reach a particular server once you have reached the correct destination network. So, this information, that means this information which is required to I mean keep track of the all the other networks, they are structured as a routing table of router X. So, what is a routing table? In a routing table what we have is that that if I given a particular say address of a particular network which may be in a remote location, we should be able to find out from the routing table that which local hop I must take next. All right. Even that is a is not an easy problem, even if you when you reduce the scope of the problem to the from servers or PCs to networks, because there are millions of networks in the world. Okay. So, theoretically in your router, I mean if you do it in a very naive fashion, you would have to keep some millions of entries, so that you can match and know that this is what to take. Of course, that is not possible, because at the same time that you want to go to the correct destination for this particular packet, at the same time you want to process the packets as fast as possible. People want more and more speed. So, the network traffic and the number of packets is increasing day by day. So, you want to do it very fast. If you have a very large table, just to look up that table will also take substantial amount of time. That is one reason. Other reason is of course, you will need a lot of memory, lot of processing power, etc. So, that will drive up the cost of the router. So, even keeping millions of entries for most routers, this is not a feasible option. So, we have to somehow do something about it. The other issues in routing, one is that the topology changes affect convergence, delay and stability. All right. Topology of the network changes all the time, because as I said the links may go down or come up, nodes may go down or come up. So, the topology is changing. So, this changes this may change the path that a particular packet takes and the path that the next packet takes in the same stream. This may affect the delay, this may affect stability and other issues are there. That is one problem. The other problem is scalability to a large number of interconnected networks or routers or links, all right, as I was talking about. So, this is still a problem. Even when you come down from nodes to networks, this is still a very large problem. And then there are other issues. So, like what is the best path from x to y? Okay. You may I mean you may be able, it may be so that from x to y 5 different routes are possible. Now, all these 5 routes are not equal. First of all, they may not be equal in the number of hops, they may not be equal in length, they may not be equal in cost, they may not be equal in the quality. Some of the route may be very unreliable, that the packet has a larger probability of getting dropped there, and so on and so forth. So, we would like to have the maybe the minimum number of hops or the minimum delay or the maximum capacity. So many things are possible. So, if possible, we would also like to incorporate the quality of the path when deciding on a route for a particular packet from x to y. So, routing consists of decide the route for each packet, that is one side, and in order to do that, the router has to have knowledge of the entire network. So, and this knowledge, as we know that this knowledge has to be dynamic, because the network topology keeps on changing. So, we have to update the knowledge of the network from time to time. Okay. So, suppose you have hosts or LANs connected to some routers like A, B, C, D, E, and then through the links 1, 2, 3, 4, 5, 6, etc., and then say the job of A, when it is, let us say the router in A, when it gets a packet from a local network which is connected to it, which may be destined for this LAN, maybe the LAN which is connected to C. So, it has to decide whether to take the link 1 or link 3. Obviously, it does not take this link, because this is where it is coming from, and this is obviously destined to some network which is sort of remote. So, it has to decide, all right. Although in this particular example, you may theoretically reach C both by taking link 1 and link 3, but then these links may be of different quality. Okay. Maybe something like A, D, E, B, C is a better choice. As mentioned earlier, these routing tables, so we have routing tables in routers, and they look somewhat like this. We may just look at one of them, it does not matter. For example, the routings from A. Now, so basically we suppose, I mean this is one form of it, okay. It may not be used exactly in this form, but let us just look at it. Suppose, so we just list the router. So, for each router, suppose you want to route to the router A, which is again local, because we are sitting on router A. For B, you take the link 1, C link 1, D link 3 and E link 1, just look at it. From A to B is link 1, okay. Maybe C is also link 1, D is link 3 and E is again link 1. This may be a better choice, and so on. Similarly, for B we will have a routing table, and C will have a routing table. One thing to note over here is that suppose you take any destination, all right, A, let us say A. Now, for A, for A is the, let us consider a tree with a root at A. Now, B connects to A through link 1 and C connects to A through link 2. So, B connects to A through link 1 and C connects to A through link 2, but obviously link 2 is not taking C to A directly, link 2 is only taking C to B, but that is the preferred path for connection from C to A. So, this way if you think about it, for each destination we have got some kind of a tree, all right. If this network was very bigger, here the network is very small. So, the tree is only 2 levels deep, but the tree could be, I mean, very deep, maybe 10-15 levels deep. So, for each destination actually we have a tree which is implicit in these routing tables which are distributed, all right. So, I mean once again that for at each node we try to see that for that particular destination this is the local link I will take, okay. As I said that the local link may not take you directly to the ultimate destination, but the local link will take you somewhere. That particular node will again have a link to what is for the same destination, what is the best link to take, and this way after some hops you will hopefully, I mean everything, if everything is working fine, after some hops you will reach the final destination, which means that, I mean some of the other nodes may be directly connected, some of the other nodes may be 2 hops away, some may be 3 hops away, etc. But overall there is a implicit tree for each destination, and for one node link of this tree is in the routing table of one particular node, all right, according to the, I mean just according to the destination. So, if there are n nodes, there are n implicit trees, and these n implicit trees are distributed over n nodes, okay. So, one link from each tree in the routing table of a particular node. So, that way you have a routing table of size n, including the root which is the local, all right. So, there is a and somehow you have to maintain this tree somehow, and that is the job of a routing protocol, and we will see different routing protocols later on, that how this tree or how these trees, implicit trees may be maintained, or rather how these routing tables have to be maintained. That is a part of the routing protocol. And then if you have such a table, then there is a question of forwarding. Forwarding means, so routing is the process of building routing tables at each router. Forwarding is the process of looking at the destination address of a packet and sending it to appropriate next hop interface of a router, which means that once through a routing protocol, if you have got a routing table, then a packet actually arrives and you have to forward it to the correct interface of that router. So, you look up this table and look up that what is the interface to which I must send and forward it. So, this routing or forwarding, these are two different and distinct parts of the router, and actually sometimes these two are divorced even more. For the time being, we take it that the routing and forwarding is taking place at the same place, and the routing table itself is being used for forwarding, although that may not always be the case. Forwarding requires access to local routing table. Sometimes forwarding table is structured in a different manner than routing table sometimes, all right. So, forwarding table is just optimized for packet lookups. Routing table optimized for routing changes, topology changes, etc. all right. So, a routing table may look like this, say net number 10, the next hop would be this IP number, because the routing table and that is working on the IP address. By the way, so this is one IP address, this IP version 4 address. So, this is contains 4 numbers, all less than 256. So, 171.69.245.10, okay, and the link cost may be there. Whereas, if for forwarding, we really do not care what the IP address of the next hop is, we do not even care about the link cost, because all these are part of the setting up the routing table. For the forwarding table, we just want to know the interface, what is the interface, local interface to which this packet has to be sent, and what is the MAC address of the at the next hop. This is what we are more interested in. So, that I mean basically you can just make your data link headers you can add and just send it over to the physical layer. This is a slightly more higher level and abstract view of processing an IP datagram in IP. Okay. So, there is this IP module. So, there is a routing table, this is the central thing. So, there is a routing protocol which may make this table. Sometimes we also use static routing, I will tell you later on what it means, but static routing for the timing, let us take it as if that somehow it has been manually configured. So, some of this stuff may have come here through a routing protocol, some of the entries may have been manually configured, all right. Now, when a packet comes from an upper layer, it will come from some transmission layer protocol, and two of the most common transmission layer protocols are TCP and UDP. We will see what they are later on, but maybe some packet has come maybe through UDP with some destination IP address in it. You look up the routing table, you look up the next hop and send the datagram, all right. Or it may have come through TCP also, the same thing, and then now there is one thing, it may be that the destination, it may be that we are talking about the processing of the IP datagram in IP that is in the IP layer, and this IP layer is present in two different places. One is that the IP layer is present in a host, regular host, let us say a PC or something. The IP layer is also there in a router. Okay. Now, the jobs of the two these things are a little different. If a packet comes from outside and then if it is a, let us say a PC, a computer, then the PC will really want to check whether the destination is, I mean it is really meant for him. If it is not meant for him, the PC is simply going to drop that packet, ignore that packet altogether. Whereas, in the case of a router, if a packet comes from outside, it looks up that I mean obviously you would, I mean usually you would not destine a packet to the router itself. So, it is destined for some other machine somewhere else. So, it will do a lookup and then actually forward it. So, in a PC the forwarding table may be disabled, whereas in a router the forwarding table will be enabled. Of course, in a PC if the packet originates from that machine itself, then it has to go out, then it is on its way out, alright, then it will send it maybe to the router or something. Okay, so then so for sending the datagram, then of course it is sent to the network layer, and so this is a sort of a very high level view of what is happening in the IP this thing. The processing of IP datagrams is very similar on an IP router and a host. Main difference is IP forwarding is enabled on router and disabled on host. Now, if the IP forwarding is enabled, if a datagram is received, but it is not for the local system, the datagram will be sent to a different system. This is for a router. IP forwarding disabled, if a datagram is received, but it is not for the local system, the datagram will be the datagram will usually be ignored. For a view at the data link layer is somewhat different. Internetwork is a collection of LANs or point to point links or switched networks that are connected by routers. So, this is the data link layer view of the IP datagram. So, there may be, as in this diagram, there may be some point to point links or some LANs etc., and they are connected, they are all connected by some routers R1, R2, R3 etc., R4 etc., and a particular host sends puts an IP datagram on the local Ethernet. This, if it is destined for outside, it will eventually reach the local router, and the router will decide whether to give it to another network. So, it may be an Ethernet network of Ethernet switches, it may be a token ring etc. Now, through different networks it proceeds through the routers to this. When you sorry. So, naturally when you look at it from a data link layer point of view, all these switches become visible, whereas at the IP layer only the routers and the networks will be of main concern. So, view at the IP layer, an IP network is a logical entity with a network number. We represent an IP number as a IP network as a cloud. The IP delivery service takes the view of clouds and ignores the data link layer view. That means, these details of these actual switches etc., they are in the data link layer view, whereas in the IP network view it will simply be a cloud. So, this is for the same network, this may be the picture with R1, R2, R3, R4. So, this is simply a cloud. Inside this, what is there is not important. What are important are all these network numbers. So, each network has some number. We will come to this network number later on. The following conditions must hold so that an IP datagram can be successfully delivered. The network prefix of an IP destination address must correspond to a unique data link layer network is equal to LAN or point to point link or switched network. The reverse need not be true. Okay. So, let us just understand this quite well, because this is quite fundamental. You have already seen examples of IP addresses. So, they are basically 4 numbers, each less than 255. So, something like say 144.16.192.53, something like that, all right. Now, in this but this may be the IP address of a particular machine, all right. As I said that in the network layer, it is not possible to handle all the machines individually, because that would make the problem really big. So, as our first step in our reduction or scaling it properly, we do not, I mean in the remote routers, we do not usually keep track of the specific IP addresses of specific machines and how to go there etc. Okay. We just keep track of how to go to that network which contains this IP address, all right. So, the IP address usually has 2 parts. Okay. The leading part, and that means the first few bits or the first few bytes maybe is a address of a network, whereas the last few bits or bytes may be reserved for a particular machine within that network. All right. So, this is how a global IP addressing scheme is there. So, this is not as neat as in telephone numbering, where it is exactly telling you the particular state, area and LDCA and particular exchange finally. So, it does not go, it is not that neat, but at least the first few bits or bytes will be will be associated with all the IP addresses in a particular network, all right, which means that if you just take that prefix part, you would know that it precisely means that particular network. No other network will have the same exact prefix, that means they will have the same network address. So, the network addresses have to be globally unique, all right, and when I say globally, I mean really globally, because nowadays our network is really spanning the entire globe. So, the first few the network address has to be globally unique. So, this globally unique this is called the network prefix of an IP destination address. This must correspond to a unique data link layer network. Okay. The reverse need not be true. That means, one data link layer network may have two different network prefixes, all right. So, let us not bother about it at the moment. So, routers and hosts that have a common network prefix must be able to exchange IP datagrams using a data link layer protocol, for example, Ethernet, point to a PPP, etc. Every data link layer network must be connected to at least one other data link layer network via a router. Each router and each host keeps a routing table which tells the router how to process an outgoing packet. The main columns, as we have already seen, are the destination addresses, where is the IP datagram going to, next hop, how to send the IP datagram, and interface, what is the output port. Next hop and interface column can often be summarized as one column, and routing tables are set so that datagrams gets closer to its destination. So, this is an example, another example of a routing table. IP datagrams can be directly delivered in direct. So, which means that these are in the local network, all right. So, they go through the interface called ETH0, maybe Ethernet 0, whereas these addresses are outside. So, they have to be this one is outside. So, this has to go through a router to a point to point link, or this may be some other network altogether. You see now the prefix has distinctly changed. If you look at this example, for example, this 10 dot, so 1.0.0/24, that means 0 to 24, anything can be there. So, for all these you just deliver it directly. Similarly, 10.1.2 is also connected directly, that means they are all in the same network. And then there is a point to point connection through a serial link on this router, so which is also maybe very closely connected to that same set of networks. Whereas, there may be other networks out in the WAN which really starts from 20 dot over here. So, for that now you again you have to go to the router and go out through some port of that router. And if you take a more global view, these different routers will be having some I mean all of them will be having routing tables. The details of these routing tables are not necessary, we know what they contain, and this is how one particular IP packet which originates here will go to a router, go to a next hop to the next router, and so on. Okay, so, say this is where the first this thing has come. So, it is sent here, it may try this and then it may go through some other paths. Processing of an IP datagram at the router. So, receive an IP datagram, then IP header validation. So, there is, as I said, this IP protocol, there is this is a network layer protocol. So, this is a different protocol. Previously we had talked about a lot of data link layer protocols. Now, we are talking about IP protocols, and for these IP protocols again once again you require some information to be exchanged between peers. So, that will once again be in a header, and for this header we will call it an IP header, because we are in the network layer, we are mainly concerned with IP for the timing. So, we will call it an IP header. So, the IP header, whether it is valid or not, or whether there is some error in that, etc., that has, so IP header has to be validated. Then if there are some options in the IP header, they have to be processed. Then parse the destination IP address, that means extract the destination IP address from this header. So, this obviously would be a part of this IP header. Then we do a routing table lookup, then we decrement TTL. This is the that means we decrement the time to live. What is this time to live? I mean, I will give you just one common example, there may be other variations of it, but we will give you the simplest example. Okay. It may so happen, as you understand, that in this distributed fashion we are trying to capture a good and consistent and correct picture of the entire global connectivity, which gives you the best connection. But this will, in practice, this may not always be possible. Why that is so? Because to get the global picture, and the global picture may change from time to time. So, to get the entire global picture in a very correct fashion sometimes is not possible. So, and if that is not so, you may have inconsistent routing table entries, and that may lead to various things. One of the things it may lead to is that it may lead to a loop in the routing table. It is not that there is a loop in the one routing table, but several routing tables, if you take them together. So, you see that a packet will go in a loop. Now, once a packet starts going in a loop, it will continue in that loop, because each time it will come to the router will see its own routing table locally, and that send it to the next one, which was hopefully in the correct path, but actually now it is in this vicious ring. So, this packet will just go on circulating there ad infinitum. Now, we cannot allow that, all right. So, one of the things to do is that we put some kind of a restriction on the number of hops a packet will take, maybe let us say 30, all right. Now, so each time an intermediate router would forward a packet, it will decrement this time to live, let us say from 30 to 29, 29 to 28 and so on. So, that after 30 hops, whichever router finds a packet with a TTL 0, he will simply drop the packet, all right. Either the packet is going in a loop, or the packets have gone very astray because of mistaken entries in the routing table and so on. Then perform fragmentation if necessary. We will see the details of fragmentation later on, but fragmentation means that, remember that over here what you are doing is that you are going from one network to another network to another network and so on. All these different networks are under different administrative control, different domains, and they may even have different data link layer technologies. Okay. Some token ring may be connected to some Ethernet, and there can be all different kinds of networks in between. Now, suppose the source had sent an IP packet which was quite large, but inside one particular network it is not possible to handle such a large packet. Okay. Now, it would be unfortunate if you drop the packet all the time, because now then it will never go through. So, what is done is that this big packet is broken up into small fragments, and the fragments are sent. Later on the fragments are again reassembled when you are in a sort of wider area. So, these fragments are reassembled into that big packet and sent along to the when it reaches the destination. Then you calculate the checksum, which is for error connection, as we know, and transmit to the next hop. Okay. And send an ICMP packet if necessary. ICMP is for Internet Control Message Protocol. So, if the routers may use ICMP packets for sort of talking to each other and sending various messages if necessary, we will see one example at least now and more later. When a router or host need to transmit an IP datagram, it performs a routing table lookup, as we have seen. So, use the IP destination address as a key to search the routing table. There is some more detail in that, we will go into that, and result of the lookup is the IP address of the next hop of a router and or the name of the network interface. So, this is the scene we have seen that. So, either you take a network prefix or host IP address or loopback address. Loopback address means that this is meant for a local consumption. So, it will go back to the same machine. So, it is coming down from a machine, it contains a loopback address, go back to the same machine. Why would somebody want to send a packet like that? Maybe one process of the host is sending some packet to another process in the same host, and it is using this network operating system part for sending that message. Okay. So, these loopback addresses are possible, or default route. Now, this default route is very important, because as I said that you cannot keep the network prefix for all possible networks in the world in this table, because then this table will then become very large. So, what you might do is that so you will have fewer entries over here for the network prefixes, and if your network is something else, maybe there is a bigger router somewhere who knows about all these networks, or there is a router we know that is more likely to know about this particular network prefix which has come. So, you send it to a default route. On this side, of course, you have the IP address or the name of a network interface. So, the destination addresses is a network address, most entries are network routes, and for host route, destination address is an interface address used to specify a separate route for certain hosts. And then there is a default route used when no network or host route matches. The router that is listed as the next hop of the default route is the default gateway. All right. Why are we calling it a gateway? Because quite possibly this is not a packet for a network which is close by. This is packet for some arbitrarily distant destination, and if this is a small router connected to this thing, so it will send it to the gateway. The gateway will in turn send it to a bigger router to find its final destination. Loopback address, routing table for the loopback address. This is the particular loopback address which is used in IP, which is 127.0.0.1. So, this is the loopback address, that means it is meant for local consumption. The next hop lists the loopback interface as outgoing interface. Now, in the now we want to actually, as I said, that we want to minimize the size of the routing table. Another thing which is done is to use a longest prefix match. Now, what is longest prefix match? Search for the routing table entry that has the longest match with the prefix of the destination IP address. That means, search for a match on all 32 bits. As I said that the IP address contains 4 integers less than 256, means that 4 bytes actually, which is 32 bits. So, an IP address is, that is IP version 4 address is 32 bit long. So, first you try to match all the 32 bits with some thing in the table. If 32 bit does not match, and then you take only 31 bits and whether you see whether the first 31 bits match, and you keep on doing it and keep on reducing till you get a match. So, that you have matched with the first entry that matches with the longest prefix where such a match is possible. So, host route loopback entry, this is host route or loopback entry 32 bit prefix match will always work over here. Default route is represented, may be represented as all zeros. So, this is a 0 bit prefix match, that means there is a 0 entry which will give you the next hop as the gateway, because now it has not matched with anything. So, then finally, this will be a 0 bit prefix match. So, suppose this is the address which has a destination address which has come in. Now, this is 128.143.71.21. Now, so of course, the 128 part would have matched with this and 143 would have matched with this, all right. But then here this is 0, this is 71. So, this will get a much better match here with this one, with the one shown in red. Similarly, 128.143.71 is also matching here, but this next next number is 21, which will match better in this rather than in with this range. So, this is where the match will take place, and you will send it to router R4. Default router of the gateway is shown as R5. So, the longest prefix match for this is for 24 bits with entry. This you can find out if you actually break up 21 into its binary form and see how many bits are matching. This is matching with this 24 bits, etc. So, datagram will be sent to R4. Longest prefix match algorithm permits to aggregate prefixes with identical next hop address to a single entry. So, this contributes to significantly reducing the size of the routing tables for internet routers. So, just look at this. Suppose for 20.2.0.0 to 16 I would have gone to router R2, and 30.1.1.0 to 28 I would have gone to R2 once again. Now, we see that the next hop is the same, and what we can do is that instead of 20 and 30, if we make this 20.0.0.0/8 and put it as R2, because of longest prefix match, 30 will also whenever something in this range also comes, that will also have a longest prefix match with this. So, it will have a longest prefix match with this rather than with this, because this is 10 over here, and this is 30 is naturally closer to 20. So, there will be a longest prefix match here. So, these two, and instead of these two entries we keep only one entry in the routing table. So, this helps in reducing the size of the routing table. Adding an interface. So, how do routing tables get updated? One is that you might add an interface. So, you have to configure it. So, it adds a routing table entry. So, this is a manual configuration. We can add a default gateway, that means for the destination, that is the default route, we can add a gateway. So, this is once again a manual updating. So, static configuration of network routes or host routes. If some particular route I want to sort of force, I might put in a static configuration over there. Then of course, the other major thing is that the update of the routing tables through routing protocols. So, whatever routing protocols happen, and we will see them in the next 2 or 3 lectures, or there may be ICMP messages from some router which may update the routing table. So, these are the different ways in which a routing table may get updated. For example, for this ICMP, when a router detects that an IP datagram should have gone to a different router, the router here let us say R2 forwards the IP datagram to the correct router and sends an ICMP redirect message to the host. Host uses the ICMP message to update this routing table. What is happening is that one particular host had sent it to one router. Okay. Now, this router sees that, well, I am not the proper person to get it from this host, that host should really have sent it to that router. So, he will now send it to that router anyway and send an ICMP message to this host, that from next time onwards when you have got this destination, please send it to that router rather than to me. Okay. So, that is the kind of message it is there. So, this is one example of how ICMP may be used. There are all different kinds of ICMP messages. So, one other thing is that ICMP router solicitation and ICMP router advertisement. Suppose when a router is switched on for the first time, how will other routers know that this router has come up? And since these other routers were not knowing about the existence of the new router which has come up, it was not sending it any message or trying anything with it at all. So, after bootstrapping, a router broadcasts an ICMP router solicitation. That means, he says that, okay, here I am, a new guy, who are the other people who are around me. So, he sends an ICMP. So, he advertises himself and he solicits ICMP messages from the neighboring routers. In response, routers send an ICMP router advertisement message Also, routers periodically broadcast ICMP router advertisement. This is sometimes called router discovery protocol, and this has to be done. Why it has to be done periodically? Because some router may have gone dead in the meanwhile. So, you have to keep current. So, by doing things periodically, you try to keep as current as possible. Lastly, routing as a graph theory problem. Okay. We can look at routing as some kind of a graph theory problem, where the nodes are the routers of a single administrative domain or different networks, edges are interconnection links, link cost related to physical distance, capacity, delay, etc. The objective is to determine minimum cost path, that is the. So, you can formulate it as a graph theory problem, and this particular graph theory problem can be handled in many ways, in different ways. So, we will see at least 2 different ways later on. So, it has some constraints, of course. It solve the minimum cost path problem in a distributed manner rather than centralized manner, and constraint 2 is react quickly and robustly to topology changes. So, these are the 2 things we would like to have. And the routing protocol requirements is that minimize routing table space. Okay, that is always with all these millions of networks working at the same time, minimizing the routing table space is always very important. This makes the router smaller or cheaper or faster. Minimize control messages, that is also important. Robustness, routers should not misroute packets, and loops and oscillations is also to be avoided, and then try to use optimal path. So, all these are different routing requirements. It is not that we can get we can meet 100% of the requirements all the time, but we try our best to do as best as we can. Now, we will just quickly go through the different approaches to routing. One is that centralized versus distributed. In centralized, one central processor collects information about the status of each link, computes the routing table for each node and distributes it. This is possible only in a small number of cases. This is not possible all the time, and obviously it is not possible over the entire internet because there is no such centralized routing. That would not work, that would not scale. In distributed routing, routers cooperate to run a distributed protocol to create mutually consistent routing table. And in distributed also there may be 2 kinds of 2 approaches to there, and we will look at both. One is that you distribute the local information only and then globally try to come to a solution. Other is that you distribute the information globally and then locally you simply route some kind of a centralized algorithm to know, because you have got now the global picture in one place, and not only in one place, in each of the places. All right. Then the routing may be source based or versus hop by hop. In source based routing, the packet header contains the entire route. If a link or a router along the path goes down, a source routed packet will not reach the destination, because the route has been fixed by the source. Okay. So, now the intermediate routers do not do anything. If the next hop is available, it will send it, otherwise it will drop it. In hop by hop, the packet contains only the destination address, and each router will sort of consult its own routing table and find out what is the next hop and then choose that next hop, whereas in the source routing it is fixed from the beginning. Loose source route is something in between, is an intermediate solution. In loose source route, what is done is that instead of specifying the entire path, you specify some sort of islands in between. Okay. That means maybe you go somewhere from here to the next here through several hops, then there through again several hops, and so on. All right. So, that is a something intermediate between strict source routing and pure hop by hop routing. The routing may be stochastic versus deterministic. In stochastic routing, each router maintains more than one next hop for each possible destination. One of these is randomly chosen. So, this is the idea is to distribute the load evenly. The load is distributed along the links. On the other hand, packets may get out of order because of this, because the packets from the same source to the same destination, the first packet may be stochastically chosen to go through this path, another may be stochastically chosen to go through this path. Okay. And the probability of choosing either this path or that path, you can make them based on some metric, okay, like the delay or something, but end result is that, and the end you may the packets may reach out of order. Okay. Once again, please remember the job, the service that the network layer is providing, it is just to send the packet from an end to end, that means from one end to the other part of the network. Okay. So, in doing that, first of all, there are so many things, this part has been said explicitly, okay, but it is also important to understand what has not been said. Okay. It has not been said that this service is going to be very reliable, which means that in the interim some router may drop a packet. So, your packet may not reach the destination at all, okay, that is one thing. So, reliability is not guaranteed, that is one thing. Another thing it has not been said is that all the packets that you send from destination A to B will reach the other end in a proper order, in the same order in which they were sent. The first packet may reach later than the second packet, because it came through maybe two different paths or maybe due to some other reason. So, once again the ordering of the packets, that is also, there is no explicit guarantee has been given, and there is, now you have to assume that there is no guarantee. Obviously, to the end application, this may not be a very happy situation at all, this may not work at all in many cases. So, in such cases where this is very important, you have to take precaution against this, or you have to put in corrections for this at some other layer. Okay. The network layer is not doing this. So, this was the idea of breaking it up into layers in the first place. Okay. In the physical layer, physical sending; in the data link layer, sending on to one hop only, and try to make it as reliable as possible through checksum, etc. In the network layer, it is just reaching the other end of the network, that means through several hops. Now, if you want to do it reliably, you have to go up one level more and then try to do something there. Okay. We will see how it is done. Single versus multiple paths. Each router maintains one primary and some alternate paths. Single path routing is used in internet to reduce routing table size. Okay. These multiple paths or stochastic, etc., they are not usually used in these routers in the internet, simply because the routing table size is at a premium. Multiple paths are used by telephone networks, as routes can easily be deciphered from the address. State dependent versus state independent. State independent or static routing precomputes the routes, and state dependent or dynamic routing uses the current measured network state, okay, which may change as the packet is proceeding. In static routing, the next state entry does not change in response to changes in network traffic or topology. In dynamic routing, it does change. Routing in the telephone exchange, of course, is very simple, as we have already seen. Under the same exchange, there is no routing. Under the same short distance charging area, a central switch sets up the connection. For trunk calls, the central switch forwards the setup request to the trunk exchange and maintains a primary and alternative path to long distance charging areas. Okay. So, we need not go into the details of this. So, we will continue our discussion with IP. Possible goals of routing algorithm may be minimize average end to end packet delay, maximize throughput, minimize average number of hops. Okay. Another way we do route is to flood. By flooding means this is some kind of a broadcast. So, a router, if it wants to flood something, it will send the same message to all the routers who are connected. Okay. Now, sometimes that may be a very nice and fast way of reaching somewhere, because when you are flooding, what will happen is that very soon this message is getting replicated at each node, and it will everything is running perfectly in a synchronous manner, it will reach the destination using the shortest possible route. The only problem is that not only one copy will reach, maybe multiple other copies will reach using different paths, and then multiple other copies will never get anywhere, but they will sort of choke other parts of the network. So, these overheads are there, but still flooding is used in some special cases. That is one reason why we want to use flooding. Another reason is that when we actually want to broadcast this to everybody, then one good thing to do is to flood it. So, every incoming packet is sent out through every outgoing line except the one it arrived on. A hop count or keeping track of previously flooded packets may be used to avoid generating infinite number of packets. Gives shortest route and is very robust, but hardly practical otherwise in many situations, but in many situations they are also practical. Flow based routing, a static algorithm that uses both topology and load for routing the traffic matrix and the line capacity matrix, and a routing algorithm is assumed to be given. So, we are not going into the details of any of these. Flow based routing, we will come to that later on when we do MPLS. Given a particular set of routing entries, the net average traffic in each link is calculated. So, you can sort of try to do some traffic optimization through this. Then we may have multipath routing. At router given packet with particular final destination, several choices for next routers are enumerated and then it is chosen in some fashion. Then multipath routing may yield more stable traffic sometimes. Alternative routes also is a similar. Dynamic routing we have already talked about, the centralized versus centralized routing. It has its disadvantages, that means it lacks some fault tolerance if routing computer goes down, centralized one. Whereas distributed routing, which is the one which is most usually used, it may use distributed some distributed algorithm like distributed Bellman-Ford, or it may use some centralized algorithm with distributed global data. So, we will look at these particular, that means the distributed routing in more detail in the next couple of lectures. Thank you. Good day. So, we have seen about basic routing, what is it all about. Now, we will go to some specific important and specific routing protocols, and the first routing protocol that we will be discussing today is known as distance vector routing or RIP, routing information protocol. So, RIP, I mean this is the this is one of the oldest routing protocol which was actually used on the internet, and it is still used in today in many places, which is based on distance vector. We will see what the distance vector is. Now, the distance vector of node x is the minimum distance from x to every other node in the network. For example, the distance vector of for A in the following graph is 1 2 2 1 1. That means, for B is a distance 1, for C it is a distance 2, for D it is a distance 2, for E and F these are distance 1. So, 1 2 2 1 1 from A, these are the distance vectors.